Hi, my name is Brooke. I am going to be presenting how I identified an unknown compound using IR, spectra, 13C NMR, and 1H NMR. We were given a molecular formula of C10H12O, which I first found the hydrogen deficiency index for using the formula 2N plus 2 minus H divided by 2, N being the number of carbons and H being the number of hydrogens. The HDI allows us to interpret the molecular formula and get us one step closer to figuring out an unknown compound's molecular structure. A key point to look for is if the HDI is greater than 1. This indicates an alkene or an aromatic ring. The reason behind it is that a aromatic ring and alkene would take the space of a potential hydrogen that could have been there if it was a fully saturated compound. In this case, I had an HDI of 5, which is a huge indicator that there is probably an alkene or an aromatic ring. Because it's a 5, I would assume an aromatic ring, so I will keep that in mind as we keep going. Infrared spectroscopy is a way that measures the absorption of energy into a specific bond, each type of bond absorbing at a different amount of energy. This is useful because it helps us determine which functional groups are present in a sample. It is measured in wavelength, and it needs a dipole moment to interact with the electric field of light. A perfectly symmetrical bond having identical groups attached on either side of it will not have a dipole moment. Another law to keep in mind is Hooke's law. And Hooke uses springs and balls, but we're using bonds and atoms. And this is saying that the vibration frequency is proportional to the strength of the bond. Stronger bonds will absorb at a higher frequency, while weaker bonds will absorb at a lower frequency. And we also see an inverse proportion relationship from the vibrational frequency to the mass at the end of the bond. So bonds with lighter atoms absorb at a higher frequency, while bonds with heavier atoms will absorb light at a lower frequency. These are key peaks to look for in the IR spectra. A very broad 32-3400 OH stretch will indicate, that OH stretch will indicate usually an alcohol. What we're looking for is we indicated that there might be an aromatic ring, which have a bunch of CH stretches. It's not one continuous CH stretch, since it's a ring and there are different environments for each different environments for each bond. So we're going to be looking for short multiple peaks within this range because they are still CH peaks, but within a ring. I just wanted to point out, though, that you see here that this bond over here is a triple while this is a double. Therefore, it is vibrating at a higher frequency. This may be a single bond, but it is a hydrogen bond, which is a very light atom, versus a nitrogen or a carbon or an oxygen, therefore is vibrating at a higher frequency. Okay, so then we also got this IR spectroscopy to identify our compound, and we do see this aromatic ring region, which is awesome, and then which is confirmation of an aromatic ring, but we will keep in mind that it could potentially be something else. This CO stretch is at 1700 cm-1 and is evidence of a possible carbonyl within the compound, which we did not know before, but now we do, and we'll keep an eye out for that. This CC stretch is good to know as well, knowing that there's going to be multiple carbon-carbon stretches, but doesn't tell us much more than that. So let's go to the next method to find out more. 13C NMR uses magnetic properties of the C13 isotope. It involves molecules absorbing electromagnetic energy in the radio frequency range. The types of information we can pull from the 13C NMR are the number of each unique carbon. Each unique carbon will appear as a single peak. Unique refers to the different environment of each carbon. So not the amount of carbons in each compound, but the amount or the type of carbon in each compound. It also will show a chemical shift, which is the location of each peak depending on the chemical environment of the carbon atom. We will also see the chemical shift increasing as electronegativity increases. That means a carbon that's just surrounded by hydrogens versus a carbon that is connected to or surrounded by an electronegative atom such as oxygen, iodine, bromine, chlorine, or nitrogen will push the compound more downfield. It happens because the electronegative atom creates a de-shielding effect, pulling away electrons from the main carbon atom, allowing for electromagnetic energy to create a larger signal. In our case, we are looking for the conformation of an aromatic ring, which will be here on the sp2 side of the field. And sorry, the left side is called the downfield, the right side is called upfield. So we're looking for a aromatic ring to appear around 120 and 140 downfield, as well as a potential carbonyl carbon signal at around 200 to 220. We will also be able to tell the other carbon and hydrogen connections from here, what kind of carbon and how many C2s and CH3s that we may potentially have in our compound. So we do see a carbonyl carbon, which is another conformation of either a ketone or an aldehyde. We do see this aromatic ring again, so I'm pretty positive we have an aromatic ring in our compound. We also see that there's this 10 ppm peak, which is evidence of a CH3 molecule. And since it's so low, it's not connected to anything electronegative. So I'm assuming it's a CH2 it's connected to. We also see in the CH2 region that there's 2 peaks, which one is pretty downfield for a CH2, meaning I think it's connected to an aromatic ring or a carbonyl carbon potentially, making the carbon itself less electron dense, and bringing it more downfield. Versus this peak right here, which I believe is within the range of CH2, and therefore I think may be connected to just a CH3. To find out more, we use the 1H NMR, which uses magnetic properties of the H1 isotope nuclei. Just like the 13C NMR, we can identify chemical shifts and the number of unique hydrogens, but unlike the 13C NMR, we have integration and multiplicity or splitting. Integration is it reveals the number of hydrogens of each type, and multiplicity is a pattern that follows the n+1 rule, which shows the amount of neighbors next to the carbon of the represented peak, which allows us to figure out the structure of how the the carbon and hydrogen connections are structured. So here we are again looking for conformation of that aromatic ring. We're going to look for conformation of a potential aldehyde, and if there is no peak, we will confirm that is a ketone, because ketones do not have any hydrogens a part of it, therefore will not have a significant peak in this spectrum. Another thing we'll be able to tell and confirm is the H3 and CH2 groups and how they are connected into the compound. So we see here, my first thing is that there is no peak up here showing an aldehyde. Therefore, I believe that we do have a ketone in the compound. Another thing I see is this 5H integration, meaning there's 5 hydrogens integrated in this peak, and also around the 7 ppm, which we see from here is going to be a aromatic ring. So that is a confirmation of an aromatic ring. We also see, we'll start down here with the 3H, which again, 3H integrated, 3 hydrogens integrated into this peak. If we go further in, we see that there's 1, 2, 3 peaks, which means the n+1 rule. So there has to be 2 neighbors plus 1, so which would create this triplet, and then so it's next to a CH2. So this CH3 is next to a CH2. We also see this integration of 2 with a 1, 2, 3, 4 peaks, a quartet. And so that CH2, which means that that N would be a 3. So the neighboring carbon has 3 hydrogens to it. So the 2CH is connected to that 3CH. Here we see that this 2H is, sorry, little sneak preview, is a singlet. And that means that that CH2 is not connected to carbons that have hydrogens. It doesn't have any neighbors. So therefore, this carbon's probably connected to the carbonyl carbon, which is a ketone that has no hydrogens involved, and an aromatic ring, which is connected to the carbon specifically that has no hydrogens connected to it. Therefore, with all the information that I got, this is the compound that I created, or the compound that I believe that I had, which is 1-phenyl 2-butanone. Thank you for listening.